Hi, welcome back to CMSC 828T. Today we'll be talking about one of the most important concepts required in order to fly a quadrotor or a drone, which is rigid body transformations and rotation matrices. So let's dive right into it. Okay, so the first question I would like to ask you is, let's say we have a quad rotor, like the one shown in the figure on the left hand side, and we also have another quad rotor on the right hand side. Do you think that these two are related by a rigid body transformation? Think about it for a minute and come back. I would say the answer is yes, because if you neglect the fact that these propellers are spinning and they flex when they spin, you can safely assume that these are rigid body transformation, assuming that all these individual pieces or components are rigid or that they don't deform as they move in space. What do you think about this? Do you think this is a rigid body transformation just like the previous case? Think about it for a minute and be right back. I think yes, it's exactly the same argument as before, and one can argue that if the propellers are not spinning or that they don't flex when they spin, you can easily argue that it's a rigid body transformation. But one might be asking now, what do you exactly mean by a rigid body transformation? So we'll have to define it more formally, but we'll be doing that shortly. So stay tuned. Okay. In order to define what a rigid body transformation is, we need to define a precursor to it. That is, what is a reference frame? First question being that. Let's take the same coordinator as we had before, and let's assume that it's in a frame reference A, which is shown in the figure right away, and you basically want to define certain coordinate frames like the one shown in the figure. Let's denote them by A1, A2, and A3. So what do you think are the properties which have to be satisfied by A1, A2, and A3 to be the basis vectors or the general vectors which denote the coordinate frame A? Think about it for a minute and be right back. You can pause the video if you want to and think about it. The easiest thing is you can relate these to analogous X, Y, and Z coordinate frames we are all familiar with. So, as general intuition says, these have to be perpendicular to each other, or in mathematical terms, they have to be normal to each other, or orthogonal to each other. Also, each of these axes generally denote the direction vectors, which means that they have a unit norm, or the norm is 1, which is exactly what is written in the slides here. So we say orthonormal reference frame, which is orthogonal, that these are perpendicular to each other, and they're normal, that they have a unit norm. And again, A1, A2, A3 can be replaced by any arbitrary notation you deemed possible, feasible. And let's consider a vector V in this A1, A2, A3 coordinate frame of reference. How do we denote this vector V in terms of A1, A2, and A3? Think about it for a second. The easiest way we can write this as a simple combination of these basis vectors. More formally, V is sum V1A1 plus V2A2 plus V3A3, where V1, V2, and V3 are the components of the vector V. In mathematical terms, this V1 is basically the vector component of V on the coordinate frame A1, and V2 on the basis vector A2, and V3 on the basis vector A3. This analogous to V dropping a perpendicular into each of these X, Y, Z axes, or A1, A2, A3 axes, and defining the coordinate vector V. So it's similar to what we learned in high school. We write coordinate frames as 2 or 3 numbers, and for 2D and 3D, this is exactly the same thing. Just put more formally in a math term. Same thing applies for any coordinate frame B, rotated, translated, whatever. It's the same thing applies. Okay. So These notations are super confusing, so we'll try to stick to some of these norms. And if something is not obvious, please try to ask in class, or please pause the video and look at it and see if that makes sense. Like generally you can try to derive things from context of what something should mean. A general rule of thumb is try to look at the sizes of these vectors, which will give you an idea. Okay, let's start with the first one. Any italics letter, a small letter, small letter will basically denote a vector or its components. So one more formulation which we'll follow in this class is a vector is vertical. It's a vertical vector. Some of the places in machine learning use a horizontal vector. In this course, we try to stick to vector being a vertical thing. And any capital letter which is italics will refer to a reference frame. Why a reference? Why is this italics? Because this is generally what is followed in the textbooks in robotics. Any capital letter which is not italics but bolded represents a matrix, and any vector which has any matrix like representation which has a superscript and a subscript represents a transformation. In this case, the transformation depicts the transformation A. Sorry for reuse of the variables. The transformation A, which is the big bold letter in the middle, of frame B with respect to frame A. This is what it represents. Okay. So now we will try to define what rigid body means more formally. Consider a rock like you would generally see. Oops, not this kind of rock, this kind of rock. Okay. So what do you mean by a rigid body? So you can consider a rock, and we want to formally define what a rigid body means, and we will come to that in the next few slides. So to define that as a precursor, we need to define what rigid body displacement means. So a displacement is a transformation of points. It's any transformation, linear or non-linear, some transformation of points. So consider the rock and pick any two arbitrary points on it. Let's say the red one is P, the blue one is Q, and the vector goes from P to Q, and this is denoted by vector V. So then we transform this rock, all the points on this rock or the whole rock, it's the same thing, into through this transformation G, such that you get P and Q. If you are carefully noticing, I have denoted the vector transform vector as G star of V and not G of V. Take a short break for about 2 minutes and think about why I would do that and why is it not G of V, and come back in a minute. You can pause the video if you want to. Okay, so it's G star of V because the points are being transformed by G. So this point will be G of P and this point will be G of Q, or this rock is going to be G of rock. But the vectors need not follow the same principle, and most likely they will not. You can also think about when would it actually be the same transformation. That's a homework assignment for you to think about. But in this case, it's not. So in the more generic case, I'm going to denote it as G star V. So the first condition which we want is basically that the length of the vector V in both the original frame, which is on the left, and the transform frame, which is on the right, have to be the same. That's the first rule which rigid body displacements have to follow. What's the second rule? Now let's consider 3 points, same 2 points P and Q before, and we also consider point R. And now the vectors between P and Q will be denoted by V, and the points between P and R, the vector between P and R will be denoted by W. And we do the same transformation G, which is linear or not, it's a linear transformation, and the vectors are going to be G star V and G star W. So the second main criterion is that the cross products have to be preserved, or that the normal to the plane of all these 3 points have to be preserved, which is denoted by this equation on the slides. Okay. Next, so to summarize, here are some points to remember about rigid body displacements. So in a sentence, rigid body displacements are transformations or mapping that satisfy these important properties. The map preserves length, like we said before. The cross products are preserved by the induced map. The rigid body displacements and rigid body transformations are used interchangeably. And if you look at any literature, if they are talking about rigid body transformations or rigid body displacements, they generally refer to the same thing. They're very widely used. Okay. Transformations generally used to describe relationship between are generally used to describe relationship between reference frames attached to different rigid bodies. So that's what they're generally used for. Displacements describe relationship between 2 points and orientation of a frame attached to a displaced rigid body. We'll talk about the last 2 points, or the fourth and fifth point, in the forthcoming slides. But just remember this for now. Okay. So to talk about the last 2 points in the last slide, we need to talk about what rigid body pose means. So let's say we choose a reference frame denoted by the frame A, which is on the left, and we want to depict the rock in frame B in frame A. So we will need to define two things. One is how it's rotated with respect to frame A, and how much it's translated with respect to frame A. So in this case, translation basically means how far the origins are in vector space, right? Okay, cool. And that's denoted by the light blue vector here. Okay, so you can think of it physically as taking the rock from B and just sliding it onto A and seeing what the difference between them is. So more formally, the orthogonal or orthonormal basis vectors B1, B2, B3 can be represented as components of A1, A2, A3, or basically each of these orthonormal basis vectors B1, B2, B3 can be represented as a vector in A1, A2, A3 space using what is denoted here by capital R with some subscripts. We'll talk about what they are later, but I think some of you already know what this is. And pause the video for a minute and think, what is the assumption I implicitly made without actually telling you guys. Okay, here is the assumption I originally made in the last slide. I assumed that the origin of both frames A and B are aligned, which is the one shown in the figure here. Consider any point P, and you want to transform the point P represented in the frame B to frame A, or vice versa. That's the end goal we're trying to solve. Okay, so the same equation as before, nothing has changed. And let's talk about notation for a minute. Let's call a matrix R, which shows you the rotation of vector space B or coordinate space B in frame A, which is denoted here by R B in A. I've tried to follow the color coding that dark blue, all the dark blue things refer to the frame B, all the light red things denote the frame things respect to frame A, and the light blue is the point. Okay, so RB in A is denoted by three vectors B1, B2, B3, which is R11, R12, R13. So same thing as written here. And I have missed a small thing here. There should be a vector A after the rotation matrix R, which I'll fix it, but sorry for the mistake in the slides. But it's correct on the right hand side, which is basically B1 transpose A. No, my bad. Actually, so the RB in A is basically the basis vectors B1, B2, B3, which is basically directly the rotation matrix. And this is going to be the vector components of A taken dot product with that of the B, with the B vector. So that's what is shown here. Okay. And the point here, one more notation sake, P in A basically refers to the point being represented in frame A. Is basically the point represented in frame B multiplied by the basis vectors of B. That's what is shown here. Or in other words, point in the reference frame A is rotation bit which takes you from frame B to frame A multiplied by the point in frame B. Sorry. And RBA can be written in two ways, which is shown here. So again, to summarize, RAB is written in these two ways, which is the same thing. Takes a point represented with respect to frame B and finds the locations with respect to frame A. And columns of R, B in A are the basis vectors of frame B represented in frame A. Okay, so for a minute we have to talk a little bit about what the properties of these rotation matrices are. So one, it should be orthogonal. That means that R transpose is I, which is equal to R transpose R. So that means The inverse of a matrix is basically the transpose itself. And we have to also enforce one more criteria, because orthogonal just says that the determinant can be plus or minus 1. But in this case, we enforce the determinant of R to be plus 1. Pause the video for a minute and think about why this is enforced to be plus 1. What is the implicit assumption I made without actually telling you guys? The implicit assumption I made is that I'm choosing a right-handed coordinate system. That is, when I take cross products, it's in a right-handed frame of reference. That's why it's plus 1. And my rotations are defined in anti-clockwise direction. If I swap any one of these two things, that is, if I make the left-handed coordinate system and choose anti-clockwise, or I choose a right-handed coordinate system and make the rotations clockwise, the determinant of R will be minus 1. And this is an important point to note, because when you want to convert from a left-handed coordinate system to a right-handed coordinate system, you will be multiplying by a rotation matrix which has a determinant of minus 1. And people who are familiar with OpenGL or any graphics would have seen something like that before. So just be careful. Generally, it's supposed to be plus 1. So just remember that. Okay. Other thing is, it should be closed under multiplication. That means that if I choose a rotation matrix R1 and a rotation matrix R2, and I multiply them together in any order, the resultant rotation matrix, or whatever matrix is, it's R3, should be a rotation matrix, it should satisfy all these properties. And the inverse of a rotation matrix, R inverse, should exist if there is a rotation matrix. So that is another condition. And I claim that set of all rotation matrices is a group. So people with math background would formally know what a group means, but people who don't, I will talk about in my next slide. So what is a group? A group is generally defined by this notation, that is G of A comma some special symbol. In this special symbol, I'm choosing a cross with a circle on it. So this cross with a circle can represent any operation. In this, for the rotation matrix case, we will choose multiplication, and that's the idea. Okay, so a group should satisfy 4 major properties. Closure, which is if I pick 2 elements from the group, and if I apply the operation between A and B in any order, and that the resultant should belong to the group G. Associativity, which everybody knows from high school math. Identity element says that there should be an element in the group G, which if I use the operation with respect to any other element, I should get back the same element. It's analogous to 0 for addition, like anything plus 0 is the same element, or it's analogous to the number 1 in multiplication, which we learned in high school. So anything multiplied by a number 1 should get back you the same number. Okay. So, and we also need to have a property about inverse element, which is if there is an element in the group, and the inverse element should also belong to the group, such that the operation between this element and the inverse element is the identity which we defined before. For the rotation matrix, we will define it's a set of all 3 by 3 matrices with the group operation being multiplication. So, and the conditions are defined here. So R transpose R should be R transpose, which is identity, and determinant should be plus 1 like we enforced before, because we assumed right-handed coordinate frame system with anti-clockwise rotations being positive. And more formally in math, this is also called as SO3. So why is this called SO3? It refers to special orthogonal of order 3. Order 3 because it's a 3 by 3 rotation matrix, all real number space. Orthogonal because each of the columns are orthogonal to each other. Special because the determinant is enforced to be plus 1, assuming that it's a right-handed coordinate system with anti-clockwise rotations. Okay. Now we need to talk a little bit about rotations about intermediate axes. So consider the axes shown here, X, Y, Z, and I rotate about the y-axis in anti-clockwise direction by angle theta. So the new coordinate frame would look like this, wherein y1 coincides exactly with y. And now I'm going to rotate about the z-axis or z1 axis, which is the intermediate new axis, by an angle psi. So the resultant axis is going to look like this. So what do you think the final rotation matrix which encompasses these two rotations will be. Let's say we know the rotation matrix which represents rotation about x-axis, y-axis, and z-axis. Let's say you have a function in MATLAB you can call and it will do that for you. Pause the video and think about it for a moment. So, as you would expect, it would be something like this. It's rotation of 2, which is the last frame, with respect to the 0th frame, which is rotation of frame 1 represented in 0 post multiplied by rotation of frame 2 with respect to frame 1, which is ry theta into rz phi. Why is that post multiply? You can easily derive it by taking vector products by the definition of a rotation matrix. I am not going to derive it. I'm going to leave that as a homework exercise for you guys to derive and find out why that is so. It's super easy to prove. Okay, just to summarize, post multiply successive rotations or transformations about intermediate axes. Okay, now let's talk about rotations about a fixed axis. Why is this important? Imagine you have some fixed frame of reference, which we generally call as world frame of reference or inertial frame of reference. That's the thing which is followed in aerial robotics or quad rotor literature. Now you want to rotate with respect to that particular fixed axis because it's easy for us and it's intuitive to understand, right? Okay. Now I'm going to rotate with respect to the fixed axis by an angle about the fixed world axis by y and the fixed world axis by z. And this is how my resultant would look like. And one more terminology here. The frame which is fixed to your quad rotor or your robot or aerial robot is generally called body fixed frame because it's assumed to be rigidly attached to your physical body, and that's why it's called a body fixed frame. Just to reiterate, the world frame or the inertial frame is a fixed frame where you want to define things in, and the body fixed frame is basically the frame on your quad rotor or your robot which moves exactly how your body moves. It's rigidly attached, and you generally want to represent your body frame in your inertial frame or world frame. Okay, so as you would have guessed, it's not exactly the same as before, and the rotation order has been swapped. So R20 is R21, it's R21 into R10, which is pre-multiplied. So we did the rotations in the opposite order. So pre-multiply successive transformations about intermediate frames. This might be a little bit too confusing, so please look at the video twice or thrice and try to derive it by hand once, so it makes it super clear for you, and please don't get hung up on mix and matching these things. So if you want to remember it, one buzzword would be, remember the word prefix, which stands for pre-multiply for fixed frames. So that's an easy thing to remember. That's a buzzword, so please remember that. Now we want to talk about Euler angles. Let's say we call intermediate rotation angles as phi, theta, and psi. That is with respect to x, y, and z axis. And I'll generally try to color code these as red, green, and blue, so it's super intuitive. Okay. Now, I would say that this is not exactly the same as roll, pitch, and yaw. Pause the video for a minute and think about why this is not so. It's generally not the same because roll, pitch, and yaw is generally defined with respect to fixed frame, and Euler angles are with respect to intermediate rotation angles. Okay. How many combinations of a convention like this, which represents intermediate rotation angles, are? Think about it for a minute. The answer is 12. It's not all combinations of angles because any successive rotations about the same axis would basically add up or subtract, and it would be the exact same value, and it would just be one transformation. So you cannot have a transformation which is x, x, y, but you can have a transformation which is x, y, x. So that's what this is talking about. And what are the advantages of using Euler angles? One, it's minimal, which is it uses 3 parameters, which is 3 angles, to depict 3 degrees of freedom rotationally. And it's super intuitive to understand because anybody, any high school kid or any primary school kid can actually understand what is going on here. What are the disadvantages? It's hard if the convention is not specified. If somebody just tells you these are my Euler angles, you cannot like just come up with what the convention was. You will have to be told that. And the other major disadvantage is the angles can flip at singularity. When you have a rotation matrix and you're trying to derive these Euler angles, when you invert and if there is a little bit of noise, you're trying to invert, the sign can flip, which is a full 180-degree flip in the convention, which is pretty bad. And this especially happens when quadrotor is doing aggressive maneuvers with flips. So we'll come up with better representations later on in the course. Okay, now we want to talk about rotations using a rotation matrix. So like we said before, if we are using ZYX Euler angles, the rotations will be post multiplied because they are intermediate axis, and it's shown as this in this slide. So please refer to Rotem to Euler or Euler to Rotem in MATLAB to make sense of this. And Wikipedia page is an amazing resource to talk or read about rotation matrices. Okay. Now, all this case, we assume that the translation was 0, but we have to still talk about translation because most of the places you will have both translation and rotation. Okay, so just to summarize it in one sentence, like we said before, rotate the transformation first and then shift the origin using translation, which is a simple vector sum as depicted in the slide here. Point in frame A is denoted as rotation of frame B with respect to A multiplied by the vector in frame B plus the origin or the translation which takes you from frame A to frame B. This is indeed the vector which takes you from frame A to frame B as shown in the figure here. And so it's super intuitive. It all comes from simple vector sums and you can derive it. So all this is super confusing, right? The rotations, the translations and all stuff. Like you would want to prettify all this to make life easy for you. And you can do that through something called as homogeneous transformations. So same formula as before, but this can also be written as a capital PA is homogeneous transformation which takes you from B to A into point capital PB, where the capital P is just one appended to any point in any coordinate frame, and it's shown here. And the homogeneous transformation is basically a 4x4 matrix where the first 3x3 of the matrix is a rotation matrix, and the first 3 elements of the last column is the translation vector, and the last row, the bottom row, the first 3 elements are 0 and the last one is a 1. And this is exactly what you would derive from the equation 1. Okay, homogeneous transformation is a matrix representation of rigid body transformation, and it's denoted as RT01 as shown here. And the homogeneous representation of a vector would be basically just appending 1 to the vector. So, and multiple transformations are made super easy if we use homogeneous transformations. So consider homogeneous transformation H1, consider homogeneous transformation H2. The total homogeneous transformation will be H1 into H2. So pause the video for a minute and think about if this is with respect to intermediate axis or with respect to a fixed axis. The answer is it's with respect to intermediate axis because it's post multiplied, and all the same laws hold here too. So if you derive the H total, it would be an algebraic mess and it would look something like this. One more important thing to note here is that the inverse of a homogeneous transformation is not the transpose like it was for rotation matrices, because you indeed have to rotate the translation vector by an inverse of the rotation matrix and translate it in the opposite direction. That's what is shown here, which is minus R transpose T. So the interpretation is that the translation of minus T followed by a rotation R transpose in the original frame, it's also the same as a rotation of R transpose followed by translation of minus T in the current frame. So pause the video for a minute and read those 2 lines 2-3 times until you understand why that is so. So it's super easy if you just look at the math, but this is the physical intuition. Okay. Now all of you might be thinking, how does this all go on a quadrotor? I mean, I really don't understand how these rotation matrices transformations, they're all super convoluted to me. I'll talk about that in the next slide. So consider an image on the left. Let's say you have a quadrotor which has a lot of sensors on them, and you basically want to control the quadrotor from merging a lot of these sensor data like you'll be doing in your future projects, but you want it, they're all physically separated to each other and they have different coordinate frames of reference. You basically want to transform them into some standard coordinate frame, generally called as the body fixed frame, which is associated with the center of mass or the geometric center of your quadrotor. So that's the idea. So the image on the right shows a snippet from my master's thesis, which I did at University of Pennsylvania, wherein I had to calibrate a lot of these sensors. There were 3 GoPros, there was a VI sensor, there were 2 Google Tango tablets, and I had to calibrate all these cameras and the IMUs on the cameras, so to transform them into one fixed frame. In this case, we transformed everything to the central GoPro or GoPro C2 as shown in the figure. And all the same transformation logic holds true here also. So this is a simple, funny joke. If you understand rotation matrices, what this is. Thank you. See you next time.